Hello, this video will deal with electron and molecular geometries, as well as polarity in molecules. So when we look at molecular structures, we're looking at three-dimensional structures. They have very specific bond angles and very specific bond lengths. When we look at the bond lengths, they're typically given in angstroms, and an angstrom is equal to 10 to the minus 10 meters. Now, bonds and lone pairs of electrons around the atom are what we refer to as electron dense regions. And these regions repel each other, so we're going to want to space them to minimize those interactions. In other words, to minimize the repulsive forces between like charges. That leads us to what we call the VSEPR theory. VSEPR stands for valence shell electron pair repulsion. It allows us to predict molecular shapes in 3 dimensions from the Lewis dot structures. So you need to be able to draw Lewis dot structures before you can predict molecular shapes. The trick is you always want to put the electron regions, which include both bonds and lone pairs of electrons, as far away from each other as possible. And when we talk about a molecule, there are 2 things to consider. The first is what we call the electron pair geometry, and that describes the distribution of the electron domains. And then we have the molecular structure, which is also referred to as the molecular geometry or just the geometry, and that deals with the distribution of the atoms in that molecule. So let's take a look at this table. What we have along the top are the number of regions around the central atom. And these high electron density regions are going to be bonds and or unshared pairs of electrons. So if we have 2 electron regions, here's our central atom, and this would be the 2 electron regions. And we would call this the spatial arrangement. We typically don't draw it this way, although it gives us a good visual. Here's an example of the line dash wedge notation. So we have beryllium in the center, and we have 2 hydrogen atoms bonded to that beryllium. So this is our 1 electron region, and here's our 2nd electron region. This molecule would be considered linear, and the bond angle would be 180 degrees. Now let's say we've got 3 electron regions. That means we've got a central atom and 3 things coming off of that central atom, either bonds or lone pairs of electrons. We would have a shape similar to this. So we've got boron in the center, and we've got 3 hydrogens bonded to that boron. We would say we're looking at what's referred to as the trigonal planar geometry. And that would have bond angles of 120 degrees. So imagine that going around in a circle is 360, and we're dividing it into 1, 2, 3 regions. That's where that 120 degrees comes from. If we have 4 electron regions, here's our central atom, but we need to consider that this is a 3-dimensional structure. So when we look at the spatial arrangement, we would notice that we've got a region that kind of goes back into the page and a region that comes out in front of the page. This is our line dash wedge notation. What we're trying to designate here is that this hydrogen is coming out of the page towards us, and this hydrogen is kind of going into the page away from us. This gives us what we call a tetrahedral arrangement, and the bond angle for tetrahedral is 109.5 degrees. If we have 5 electron regions, we've got the central atom and 5 atoms coming off that central atom, we would have a look something like this, and we'd be talking about a trigonal bipyramidal arrangement. Now, tri means 3, bi means 2. So collectively, 3 plus 2 equals 5. And we have 5 things coming off of the central atom. Just a way to remember that. The bond angles will be 90 degrees if we were to look from top to side. And it would be 120 degrees if we were to look around the center, similar to what we had here. So wrapping around the center of this molecule is 360 degrees, and we're dividing it into 1, 2, 3 regions. If we have 6 electron regions or 6 electron domains, we have a central atom and 6 things coming off of that central atom. Something like this. And again, these wedges mean the fluorines are coming towards us, and these dashes kind of mean they're going back into the page. This shape would be referred to as octahedral. Now, this is a little bit misleading because octa means 8. You might assume that means there are 8 things coming off the central atom. That's not what the octa means in this name. If we were to look at this shape, it's essentially an 8-sided figure. That's where the octahedral comes from. The bond angles would be 90 degrees in along here and 180 degrees here. Again, when we talk about electron pair geometry, it determines the electron domains, and the molecular geometry tells us about the distribution of atoms. Sometimes these two terms are the same, and sometimes they're not. So let's look at this as an example. We've got NH3, which is called ammonia. We've got 3 bonding pairs of electrons and 1 lone pair of electrons. So our spatial orientation would look something like this. So we've got our bond here, our bond here, and our bond here. And then we have room for the lone pair of electrons around that central atom. That would give us a tetrahedral electron geometry. But these electrons are so small that we really don't see them in the molecule. This is what we would really see. And we would call this the molecular geometry. We've got 3 things coming off the central atom, so we would use the prefix tri. And because we have this lone pair of electrons here, it's going to make this molecule look more pyramid shape. So this is called trigonal pyramidal for its molecular geometry. Now, if these are 4 bonds, we said the bond angle is 109.5. But in NH3, we have a lone pair of electrons. And those lone pair of electrons are going to repel, and they're going to force the bonding pairs of electrons closer together. So instead of having a bond angle of 109.5, we're going to have something a little less than that, about 107 degrees. And this distortion from the given angles occurs when we have lone pairs of electrons and we have multiple bonds. So when we look at this repulsion that takes place, the greatest repulsion we would have would be between 2 lone pairs of electrons, followed by a lone pair of electrons and a bonding pair of electrons. And the weakest repulsion would be between 2 bonding pairs of electrons. Now, we also have repulsions between pairs of electrons and triple, double, and single bonds. There's the least repulsion in single bonds. We have more of a repulsion with double bonds, more of a repulsion with triple bonds, and lone pairs of electrons have the greatest repulsion. So the presence of lone pair of electrons are going to change the bond angle because they repel more. And because of that, they're going to change the molecular structure, or the molecular geometry. So we're going to kind of expand that original table we looked at. If we have 2 electron pairs, 2 electron regions, or 2 things coming off the central atom, we would say that we're looking at a linear electron geometry, and we would also have a linear molecular geometry. But we have something a little bit different when we look at 3 electron domains. Perhaps all three things coming off the central atom are bonding pairs of electrons. The electron geometry and the molecular geometry would be the same, and we would call that trigonal planar. And the bond angle would be 120 degrees. But let's look here. Now we have two bonding pairs of electrons and a lone pair of electrons. This lone pair of electrons is going to repel more than these bonding pairs are. That's going to decrease our bond angle to something less than 120 degrees. It depends on the atoms that are involved. So just saying less than 120 degrees is fine. And our molecular geometry would be considered bent or angular. So this structure has a trigonal planar electron geometry, but a bent or angular molecular geometry. Now let's look at 4 electron domains. If we have our central atom and 4 atoms coming off the central atom, we know that our shape is going to be tetrahedral. Okay, that would be our electron geometry and our molecular geometry. Our bond angle would be 109.5 degrees. But if instead of having 4 bonding pairs of electrons, we have 3 bonding pairs and a lone pair of electrons, this lone pair of electrons is going to have more repulsion. It's going to force the bonding pairs of electrons closer together, and our bond angle is going to be less than it was before. That's going to cause our molecular geometry to change as well. We have 3 atoms coming off the central atom. A lone pair of electrons forces those atoms closer together, and our shape would be trigonal pyramidal. Would almost look a little bit like a pyramid. Now let's say we've got 2 lone pairs of electrons and 2 bonding pairs of electrons. Well, 2 lone pairs of electrons have even more repulsion, so our bond angle would be even less than 109 degrees. And we would say that our molecular geometry would be bent or angular. Now notice that the bond angle here would be greater than the bond angle here because we have 1 lone pair of electrons repelling here versus 2 lone pairs of electrons repelling here. Now let's look at 5 electron domains. If they are all bonding pairs of electrons, our electron geometry and our molecular geometry will both be trigonal bipyramidal. Remember again, that 3 plus 2 gives us 5. But if we have 5 electron domains and one of them is a lone pair of electrons, that lone pair of electrons is going to repel the bonding pairs, and our shape is going to be referred to as a seahorse or a seesaw molecular geometry. I see seesaw a lot more often than seahorse or sawhorse, sorry. Now let's say we've got 2 lone pairs of electrons. That's going to give us a T-shaped molecular geometry. If we have 3 lone pairs of electrons and 2 bonding pairs of electrons, now our molecular geometry will be linear. Last, we have a possibility of 6 electron domains. If all of those are bonding pairs of electrons, our shape, our electron geometry would be octahedral. And our molecular geometry would also be octahedral. And again, remember that octa refers to the 8-sided figure, not the fact that we have 8 atoms around the central atom because we only have 6. If one of our pairs of electrons around the central atom is a lone pair of electrons, our electron geometry would still be octahedral because we've got 6 electron domains. But our molecular geometry would be referred to as square pyramidal. And the last scenario we can see is if we've got 6 electron domains, 4 of them are bonding pairs and 2 are lone pairs of electrons. It would be an octahedral electron geometry, but we would refer to the molecular geometry as square planar. Now, this is super hard to kind of visualize. We do have some simulations that you can look at. And there are some supplemental videos you can also look at that have three-dimensional moving images, which may make this a little easier to visualize. So let's kind of talk about each of these again and look at the molecular shapes in a little more detail. So if we were to have a central atom and four atoms coming off of that central atom, we're looking at a tetrahedral electron geometry. If all four are bonding pairs of electrons, the molecular geometry is tetrahedral. If we have one lone pair and three bonding pairs, the molecular geometry is trigonal pyramidal. And if we have two lone pairs of electrons and two bonding pairs of electrons, our molecular geometry is bent. If we have 5 electron domains, our electron geometry would be trigonal bipyramidal. And if they're all bonding pairs, the molecular geometry is also trigonal bipyramidal. If we have one lone pair of electrons and 4 bonding pairs, it's seesaw for the molecular geometry. If it's 2 lone pairs and 3 bonding pairs, it's T-shape. And if it's 3 lone pairs and 2 bonding pairs, it's linear. Last, we have 6 electron domains. That would give us an octahedral electron geometry. If they're all bonding pairs, the electron geometry and the molecular geometry would be the same. If we have 1 lone pair and 5 bonding pairs, the electron geometry is octahedral, but the molecular geometry is square pyramidal. And if we have 2 lone pairs of electrons and 4 bonding pairs, our electron geometry is octahedral, but our molecular geometry is square planar. I would learn them in these groups. It makes it much easier than trying to learn each individual molecular geometry. Here are some examples. Let's say we've got boron trifluoride, which is BF3, and phosphorus trifluoride, which is PF3. They look like they have the same basic structure, but we don't know the electron geometry or the molecular geometry unless we start by drawing our Lewis dot structures. From there, we can determine how many electron domains there are, how many lone pairs of electrons and bonding pairs of electrons, and then we can determine the electron geometry and the molecular geometry. So let's start with BF3. Okay, BF3 would be drawn like this for its Lewis structure. We've got 3 electron domains. So the electron geometry would be trigonal planar. If we looked at the molecular geometry, there are no lone pairs of electrons. And whenever you have no lone pairs of electrons, the electron geometry and the molecular geometry will be the same. Now let's look at PF3. So when we draw the Lewis structure, it will look like this. Notice that when we draw it, we're going to see that there are 3 bonding pairs of electrons, and there's that lone pair of electrons. We don't know this lone pair of electrons is there just by looking at its formula. We have to draw the Lewis structure in order to determine that. So there are 3 bonding pairs and 1 lone pair of electrons around phosphorus. That means there are 4 electron domains. That means our electron geometry is tetrahedral. This lone pair of electrons will repel and force the bonding pairs closer together. So our molecular geometry would be trigonal pyramidal. Now let's look at these examples. We have NH4 plus, H2O, and NH3. You might want to stop the video and practice drawing the Lewis structures and see if you can identify the electron and molecular geometries. So here's our ammonia, NH4. We've got nitrogen, and we've got 4 hydrogens bonded to the nitrogen. Again, because it's an ion, we put the brackets and we've got that charge there. Since there are 4 electron domains, the electron geometry is tetrahedral. And since they're all bonding pairs, the molecular geometry or the molecular shape will be the same as the electron geometry. So it would be tetrahedral. Now, here's water. Again, we can't really tell what that Lewis structure looks like until we actually draw it. We end up having 2 lone pairs and 2 bonding pairs around oxygen. That's 4 electron domains. So it's a tetrahedral electron geometry, just like NH4+. The difference is it has 2 lone pairs of electrons that will force the bonding pairs of electrons closer together, and our molecular geometry or our molecular shape would be bent. And if we look here, we've got NH3. When we draw it, we've got 1 lone pair and 3 bonding pairs of electrons. So it's a tetrahedral electron geometry. But with this 1 lone pair of electrons, the molecular geometry is trigonal pyramidal. I'm not sure what actually happened to the rest of this here. So it should say trigonal pyramidal for the electron geometry or the electron shape. So here we have just a couple more practice problems. We've got SO4 minus 2, SF4, and BrCl3. Again, you might want to stop the video and practice making the Lewis structures and then see if you can identify the electron and molecular geometry on your own. So when we draw our sulfate, it should look something like this. We've got 4 electron domains. They're all bonding pairs of electrons. So the electron geometry and the molecular geometry are both tetrahedral. When we do SF4, we're going to see that there's a lone pair of electrons in our structure. We have 1, 2, 3, 4, 5 electron domains coming off of sulfur. That means it's trigonal bipyramidal electron geometry. But because we've got a lone pair of electrons, our molecular geometry would be seesaw. And for our last one, we have BrCl3. When we draw it, we end up with 1, 2, 3, 4, 5 electron domains, similar to what we had over here. So that gives us a trigonal bipyramidal electron geometry, but with these 2 lone pairs of electrons, the molecular geometry or the molecular shape is going to be referred to as T-shape. So what happens if we have more than 1 atom in the center of our molecule? We would treat each atom with more than 1 bond as a central atom. Here's an example. Hydrogen here wouldn't be considered a central atom because it's only bonded to the nitrogen. Oxygen wouldn't be considered a central atom because it's only bonded to the carbon, but the nitrogen and the carbon and the oxygen would be considered central atoms, and we would have to identify the geometry around each of those structures. So let's look here at the nitrogen first. We've got 1, 2, 3, 4 electron domains. That means it's a tetrahedral electron geometry, but because of this lone pair of electrons, the molecular geometry around this nitrogen would be trigonal pyramidal. If we move on to carbon, carbon has 4 electron domains. That means it's got a tetrahedral electron geometry. And because there are no lone pairs of electrons, the molecular geometry will be the same as the electron geometry, which is tetrahedral. Now, if we were to look at this carbon here, now we've got 1, 2, 3 domains. Even though this is a double bond, it's counted as 1 domain. That means we're going to have a trigonal planar electron geometry. And since there are no lone pairs of electrons, it would also have a trigonal planar molecular geometry. Now, if we wanted to talk about the shape around this oxygen, we've got 2 bonds and 2 lone pairs of electrons. That's 4 electron domains. That would be a tetrahedral electron geometry. But because there are 2 lone pairs of electrons, the molecular geometry would be considered bent. Now let's look at these AX4 and AX3E just to make sure we understand what that means. The A just stands for whatever the central atom is. The X stands for the atoms that are coming off of that central atom. And the E stands for the lone pairs of electrons. So if we were to look at nitrogen, okay, the nitrogen is considered the A in that part of the structure. The hydrogen here, and carbon here would be our X3 part of our general structure. And then the one lone pair of electrons would be here. So if we were to look at the oxygen, we've got one oxygen, two bonds, and two lone pairs of electrons, and that's where that AX2E2 comes from. So if we wanted to make a better representation of what this molecule would look like, we would want to make this look a little bit more trigonal, pyramidal. So this hydrogen we want to show going back into the page, and this hydrogen we want to show coming out of the page. We want to show this a little bit more tetrahedral. So this hydrogen's coming out of the page, and this hydrogen's going back behind the page. This would be on the same plane, so we don't have to worry about those wedges and dashes. And this would be along the same plane as well. Last, we need to talk about dipole moments and bond dipoles. So as a review, when we talk about polar covalent bonds, we're talking about an uneven sharing of electrons between two atoms. That leaves partial charges on each side of the bond. The charge separation gives us what we call a dipole moment. And the dipole moment is a vector because it has a magnitude and it has a direction. And when we talk about the dipole moment, it's directly proportional to the magnitude of the charge and the distance between the charges. So let's look at this bond here. We've got carbon bonded to hydrogen. Carbon is more electronegative. The electrons are going to be drawn closer to the carbon. So our dipole moment is going to go in this direction. So we've got our arrow going in this direction towards the more electronegative element. And there's almost a little positive sign here, which would be on the less electronegative element, which would be the partial positive region. Now, if we were to look at the size, the magnitude of this arrow compared to this arrow is much bigger. And the reason is when we look at this polar covalent bond, fluorine is more electronegative than boron. So the electrons are getting pulled closer to the fluorine. And because there's a bigger difference in electronegativity, the magnitude of the dipole moment is going to be greater. So the arrow is going to be longer. So what does that mean about molecules? Nonpolar molecules either do not contain any dipoles at all or very small ones, or they have dipole moments that cancel out. So if we look here, we've got two chlorine atoms. They're going to be sharing a pair of electrons equally between them. There's no dipole here. This is a nonpolar covalent bond. The molecule would be a nonpolar molecule. Now, if we were to look here, this is carbon, and it's bonded to three hydrogens. Carbon has a greater electronegativity, so we do have a dipole moment here, 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 and here, all facing in towards the carbon, but they end up canceling each other out, and the molecule is nonpolar, even though the individual bonds have a dipole moment. Or if we were to look here at carbon dioxide, this bond is a polar bond. Oxygen has a higher electronegativity, so the electrons are drawn closer to the oxygen. And here, the electrons are being pulled closer to the oxygen. So each of these bonds has a dipole, but they end up canceling each other out, and the molecule is nonpolar. On the other hand, polar molecules have dipole moments on their bonds and they don't cancel out. So if we were to look at this molecule here, which is water, this is a polar covalent bond. Oxygen is more electronegative than hydrogen, so the electrons are getting pulled in this direction. This is a polar covalent bond, so the electrons are being drawn in this direction and they don't cancel out. So the molecule overall will have a dipole moment in this direction. So this side of the molecule is going to be more negative than this side of the molecule down here. So why do we care? Well, nonpolar molecules tend to dissolve in other nonpolar solvents, but they remain separate from polar solvents. They also tend to have lower melting points and boiling points because they have weaker attractions between the individual molecules. So we can separate them out pretty easily. So this would be maybe water and oil, and they don't mix. Polar molecules, on the other hand, dissolve in polar substances like water. They tend to have higher melting points and higher boiling points because they have stronger forces between the molecules. And they tend to orient themselves in an electric field where the partial positive end of the molecule would be attracted to the negative end of an electric field, and the partial negative would be attracted to the positive region of that electric field. So let's look at these examples and decide whether or not the molecules are polar or nonpolar. Again, we have to start by drawing the Lewis structure, and then from there decide whether the bonds are polar or nonpolar and whether they are canceling each other out or not. So this would be xenon tetrafluoride. It has 4 bonding pairs and 2 lone pairs. That's an octahedral electron geometry and a square planar molecular geometry. It's a fairly symmetrical molecule. It doesn't have a positive and negative end to it because even though these bonds are polar bonds, they end up canceling each other out. So this is a nonpolar molecule. If we were to look at sulfur tetrafluoride and we draw the Lewis structure, it's going to look a little bit different because now we've got 5 electron domains, 4 bonding pairs, 1 lone pair. Because of this lone pair of electrons, this isn't going to be a symmetrical molecule. So we've got these polar bonds, which are pulling the electrons towards the fluorines, plus we've got this lone pair of electrons. That's going to make this molecule a polar molecule. And if we were to look at bromine tetrachloride, our molecule would look something like this. We've got 5 electron domains, 2 lone pairs, 3 bonding pairs. That's going to give us a T-shaped molecule where we don't have a symmetrical molecule. This end of the molecule is going to be more negative than this end due to the lone pairs of electrons. So this molecule would be a polar molecule. And again, there are supplemental videos that you can watch. There are online simulations that you can kind of look at and play around with to help you with all of this information.